Hello everyone, welcome to our discussion of section 5.5, which is the last section we will be covering in this course. Now, the substitution rule is a rule that we use when we have integrals that are too complicated to integrate with the methods we've learned so far. So as you can see, these are three examples of such integrals that can be too complicated using those methods, or for some of them we don't even have a direct method. So the substitution rule entails, we can apply it to both indefinite integrals as well as definite integrals, as you can see as I move up this slide. If we have an indefinite integral, then if possible, we want to break up the original integral into pieces. When I say if possible, if it's not possible, then this integral is not going to be a candidate for application of this substitution rule. So applying this, when we want to use the substitution rule, we assume that it's possible to write one piece of the integral in terms of the derivative of the other piece. If that's possible, then this method will apply. So whether we integrating an indefinite integral or a definite integral, we have to do that part. Then we use u. We can use any letter really, but in your book they use the authors use u, and that's what I will talk about. Use u to substitute for the appropriate term, and use du to substitute for dx equivalent. So in other words, you can just, sometimes you can substitute for dx directly with du, but not often. Most usually you can substitute for dx equivalent, or when I say dx equivalent, I mean dx and some other term. So maybe 4x squared dx. So you can substitute usually du for that whole equivalent of dx. So 4x squared dx, or 1 over 1 plus x squared dx. Usually that's what you'll have to do. But sometimes, yes, direct substitution of dx with du can happen. And that step is also the same whether we're using integrating an indefinite integral or a definite integral. And if we're integrating an indefinite integral, then after that step, after this step, we will integrate easily. But if we're integrating a definite integral on this side, then we have to do something more. We'll have to convert the limits of the integration. Remember, for definite integrals, there are lower and upper limits of the integration for definite integrals. We need to convert those limits which were originally used for dx. We need to convert them to apply to du, because we have a new variable u. Therefore, those limits, original limits for dx, will not apply. We need to convert them. This is for definite integrals. And once we do that, then we can integrate easily. We will do plenty of examples, so you'll see exactly how this works. Now, a couple of rules that we have, that these are, again, make integration simple for us. So let's go over them. Integrals of symmetric functions. So if you have a continuous function f over some closed interval negative a to a, and if that function is even, remember in Math 126 and even Math 124, and even Math 127, we remember that even function is a function such that if you replace x with minus x, you will get a number that is, or an expression that is equivalent to f of x. That is, if you replace x with minus x, and it's as if nothing happened, then that function is said to be even. So f of n negative x is equal to f of x. Okay. Now, if we're integrating an even function like that from limits that are equal but opposite in sign, negative 2 to 2, negative 4 to 4, negative 5 to 5, something like that, and the function is even, then we can simply say, oh, twice that, and change the limit from going from 0 to a. So we can make that switch from this type of integral with lower and upper limits like this to one that is twice an integral such that the lower limit is 0 and the upper limit is the upper limit of the original integral. Okay, so that's when f of x is even. Just remember that. So maybe I should do that. So if f of x is even. Now, if f is odd, again, we talked in previous classes what we mean by an odd function is such that if you replace the x with minus x, or replace 2 with minus 2, then the value of the function changes such that it's as if you multiply that whole original function by a minus 1. So if you evaluate the original function at 2 and you get, say, 8 as the final result, then if the function is odd, it's as if you say replace the x with minus 6 and then you'll get minus 8. That's true for all odd functions because they're symmetric with respect to the origin, as we learned courses ago. Now, if that's true, and we are integrating such an odd function from negative a to a, some continuous where function f is continuous over this closed interval, then that integral is equal to 0. It's simple, especially when you take classes such as Math 283 or Calculus 3, and even in Calculus 2, this simplifies many integrals. And at this point, we're just introducing it. Maybe I have one example that shows how this works too, but the main application of it will come in higher calculus classes. Okay, so I wanted to introduce these two identities as well. So after that, then let's get to some examples, which I know all of us are in favor of. Again, I know a lot of times I forget, but once I go through a couple of examples, after that, the third example and beyond, please don't forget to pause the video, write down your own solution, and then come back to the video to see how this works. If you do that, then you'll learn this at a much deeper level and much faster. Okay, so we want to evaluate the following integrals by making the given substitution. So in these few examples, we are told for which terms we need to make a substitution. But usually, you are not given that information. Usually, you'll have to determine if there are terms for which you can substitute. And earlier I said that's when one piece of the integral is the derivative of the other piece of the integral. That's when this substitution rule will easily apply. So in these few examples, we are given that information, but not often. We'll have examples of both kinds. Okay, so we want to integrate, this is, by the way, an indefinite integral of x cubed times 2 plus x to the 4 to 5th power dx. And we want to make a substitution here with u equaling 2 plus x to the 4. Okay, so we are given that this time. But usually this piece is missing. We'll have to determine what here needs to be u. That will be up to us. All right, so if we take u as that, then immediately we'll have to calculate du, right? So we have u given is equal to 2 plus x to the 4 power, right? Then du dx would be, derivative of 2 would be 0. Derivative of x to the 4th would be 4x cubed, right? As soon as I write this, notice the x cubed here. So the derivative of this piece inside the parentheses is equal to a piece of this, whatever is outside of this parentheses, namely x cubed. So let's modify this a little bit. So what if I multiply both sides by dx? We can do that, right? That's the beauty of this notation du dx, which was invented by Leibniz. So it makes integration a lot easier in situations like this. So multiplying both sides by dx, what do we get? We get du equals 4x cubed dx, right? On the left side, dx is gone. Now, if we compare what we have in the original expression with what we have so far, it looks like if we multiply both sides by 1 over 4, we're going to be able to get x cubed dx, right? So then we can replace x cubed dx by 1/4 times du. Because you can't make the substitution for dx with du right away. I hope you can see why not. Because if you substitute for dx with du, which is this expression, then you have 1/4 here, and multiplying 4 on the other side that is extra, that you don't have in the original expression. You need to get rid of this 4. How do we do that? By multiplying both sides by 1 over 4. In other words, if we say 1 over 4 times du on the left is equal to multiplying both sides by 1 over 4, right? So we'll get x cubed dx. Okay? Now compare what's outside of this parentheses, x cubed dx, with what we have. X cubed dx is equal to 1/4 du. Now we can substitute for x cubed dx as well as what's in the parentheses. So let's do that. So after all that, we can write this original expression as follows. We can write the integral of u, this piece was u, right? We were given that. So u to the 5th, but we have then, well, let me do it this way. So we have x cubed dx, which are replaced by 1/4 du. So let me write it like this, 1/4 du, right? X cubed dx are replaced by 1/4 du. And I just put a space here because I want to just initially write this, replace or substitute for each piece in the same order. Then we can change the order. But in that order, I'm replacing everything. Now, for the middle piece with the parentheses, that was u, right? U to the 5th power. So now we've applied the substitution rule. But now this is considerably easier to integrate than the original expression when you have an x cubed on the outside and an x to the 4th on the inside of a binomial that is raised to 5th power. Much, much easier to integrate this. Okay. Again, note that this is an indefinite integral, so we don't have to worry about the lower and upper limits, but we will when we get to the integration of definite integrals. Okay, so now let's integrate. We know how to do this, right? This just add 1 to that power and divide this expression by the new power. So let's do that. So we have 1/4 times u to the 6th power divided by 6, right? Plus, of course, because this is an indefinite integral, plus c. Okay, now that we've integrated this, now we can replace u with what we had. So basically this would simplify to 1/24, right? 4 times 6, 1/24, times u to the 6th power, u being that piece. So 2 plus x to the 4th to 6th power plus c. See how easy that was, right? And just try integrating this without this substitution rule. It'll be extremely complicated. Okay, so this is that. Let's do another example. So let's do this one as part B. Again, in this example, we are given the term for which we're substituting. So this is cosine cubed theta sine theta d theta u equals cosine theta, right? So we are told substitute for the cosine theta piece with u, which would make this u cubed. But now, as you saw in the first example, as soon as we've established what is it that we're substituting for, we need to calculate du dx, right? Or in this case, du d theta. Okay, so if that's the case, then we have, and this is the solution, if u equals cosine of theta, then du, right? We know how to take the derivative of cosine theta, right? It's minus sine theta. So minus sine theta, of course, d theta. Now, can you make a direct substitution for d theta using this with du? No, you can't, because here you have sine theta d theta, which is positive. There's no negative here. But du, if you put du there, you're substituting with an extra minus into this integral. So therefore, minus, we multiply both sides by a minus. Minus du is equal to sine theta d theta. Now you have an equivalent for sine theta d theta, right? It is minus du. Now we can substitute this into that after, of course, we've substituted for cosine of theta. Let's do that. So this would be integral of, and I should maybe move this up a little bit, integral of u, because u is cosine theta, u cubed, right? So u cubed, instead of cosine cubed theta, we have u cubed. Instead of sine theta d theta, we have, what do we have? We have minus du, minus du. Okay? Now this minus, as you know, we can bring in the front. So let's do that. So we have minus integral of u cubed du. Now, how easy is that to integrate this piece? Very easy, right? Let's do that. So we have, oops, let me move this up. I have to watch not to go off the screen there. So then we add 1 to this power, divide by the new power plus c, because this is an indefinite integral. So minus u to the 4 over 4 plus c. Now let's replace u, since we've already done the integration, right? All we have to do is replace back in u with cosine theta, and we are done. So we write down minus, that's just 1/4, 1/4 cosine theta to 4th power plus c, but you all know that this power applies to the cosine. We can write minus 1/4 cosine 4th to the 4th theta plus c. Okay, and I need to also box my other answer. So here is the final integral, and also I need to do the same thing here. You notice how easy it is to apply this rule? Of course, the prerequisite is that a piece of this integral can be written in terms of the derivative of the other piece. All right? So we took this as u, and then we wrote this piece as the derivative of that. Only then we can apply this substitution rule. Okay, so let's see. Let's do another example of this kind where the substitution element has been given to us. Okay, so let's call this, I guess that was b, so this would be c, and we want to integrate secant squared of 1 over x divided by x squared dx, where u is equal to 1 over x. Okay? All right, so once again, we're given that. Now, if you take a look at which piece of this integral is the derivative of u equals 1 over x, you can see that we have the derivative of 1 over x is minus 1 over x squared, right? We've done that. We've taken that derivative many times before. So in this case, we have an x squared in the denominator here, but a minus is missing from that expression. We can easily take care of that. So if u is equal to 1 over x, then du would be minus 1 over x squared dx. Okay? And therefore, so notice that we cannot directly substitute for dx over x squared. We have a minus here. So in order to be able to make the substitution, we have to multiply both sides by a minus. Therefore, minus du is equal to 1 over x squared dx. Okay, now we can easily substitute. So what happens here then? Well, we simply substitute for 1 over x with u, and then integrate secant squared u, which is very easily done because it's just we have a tangent of u. We already have a technique for that. So let's do that. Okay, so we have that would be equal to integral of secant squared instead of 1 over x, right? Let me bring this down a little bit. Instead of 1 over x, we have u, right? Let me put it in the parentheses. And then the rest of this, instead of 1 dx over x squared, we have minus du times minus du. And of course, that minus can come in front. So we have minus secant squared u du, right? And then recall that integral of secant squared x dx is equal to tangent of x. Okay? We already know that. So let's apply that to this, and then we end up with, therefore, we end up with, but we have a minus in front, so minus tangent of u plus c, of course, because this is an indefinite integral. But then u was a substitute. The original expression is 1 over x. So we can bring that back and plug it in, and we have minus tangent of 1 over x plus c. And there we have it. Okay? So very useful integration technique this is. All right, so let's change the examples in a little bit so that we are not given this, but we need to figure it out. Okay? Let's do that. So in this example, we want to select an appropriate substitution term and evaluate the following integral. So we're going to do several examples of this type. And I hope that after that first couple examples, you've been pausing the video and struggling with this if you have to even, but hopefully not, and getting the same answers that I have been getting. So I'm hoping that, and I'm counting on you to pause the video before you see my solutions, and I thank you for that. If you do that, it will make my job of teaching this material easier. Okay, so let's use this example then. In this case, we have the hyperbolic sine x times hyperbolic cosine of x dx. Now, this should be easy, right? To pick a substitution term as they want us to, right? Select an appropriate substitution term. It should be easy because we know that hyperbolic cosine is the derivative of the hyperbolic sine, right? So that's easy. It's an easy pick for us. So let's do that. And please pause the video before you see this solution. So I'm hoping you've done that, and now you're back. So we pick u equal the hyperbolic sine of x, and that means that du is the hyperbolic cosine of x dx. Now in this case, can we make a direct substitution for dx with du? Yes, because you have the hyperbolic cosine x times dx on the other side. So you can replace these two terms with a simple du, right? For these two terms, you can simply say du, because given this u, the du is going to be that. So that's great. So let's do that, and then we'll substitute for this as well. So then we have integral of, we took hyperbolic sine x as u, so we have u squared, right? Because that's hyperbolic sine x squared. So u squared, and all of that is du, so du. Now look at this. It doesn't get any easier than this, right? For us to integrate. Add 1 to the power, divide the expression by the new power. So you have u cubed over 3. u cubed over 3 plus, of course, c, because we have an indefinite integral. So furthermore, let's replace u with what we should. And we took u as the hyperbolic sign. So we have hyperbolic sign of x cubed, right, divided by that, plus c, and of course, let's put it in a more concise way. So 1/3 hyperbolic sign, cubed x plus c. And that would be our final answer there. Okay, like that. All right. So let's do another example of this kind where the u is up to us to pick. So suppose we have sine of natural log of x over x. As soon as I write this x, I know some of you, if not all of you, recognize as this dx over x as the derivative of natural log of x, right? So that's an easy pick too. Maybe you should use that as a hint and solve this. So pause the video at this point. And once you're done, you're welcome back, and then hopefully our answers agree. Okay, so let's make that substitution. Recognizing that the derivative of natural log of x is 1 over x, let's pick our u as natural log of x. And therefore, we have du as 1 over x dx. Okay. In this case, once you're done with this, can you directly substitute for dx over x with du? Yes, we can. Right? Dx over x, we can directly substitute for that with du. Right? In other words, I mean, I didn't do this before, but let me do it this time. So if you break that up into pieces of sine of natural log of x times dx over x, you can substitute for this piece with du, right? That's dx over x, du. And with this, you can substitute for natural log of x with u, and integration of sine of u is extremely easy to accomplish. So let's do that. So this will be sine of u du after we make all the substitution. Okay, so integral of sine of u will be cosine of u, but because we have a positive, we know that derivative of cosine of u, it's going to be minus sine of u, but we don't have a minus. That means the original expression should have had a minus in front of it. So minus cosine of u, right, plus c. Right? Just because this is positive, if it should have been negative. If you're taking the derivative of cosine of u to get that, you should get minus sine of u. But it's positive, so the original expression has a minus in front. Okay, must have had that. Okay, so that's that. And then, of course, the last step is, what do? We replace for u with the original expression. Because the substitution is just an intermediary for us to facilitate the integration process. Okay, so let's do that. And we get minus cosine of natural log of x plus c. Okay, that's that. Let's do one example with involving tangent. Okay, so that way we cover everything. We covered natural log, sine, and before that we covered hyperbolic sine and hyperbolic cosine. So you have a good combination of examples from which you can see how this process works. Okay, so then this should be part C, and we want to integrate inverse tangent of x divided by 1 plus x squared dx. Right? So right away you should recognize that the tangent derivative of the inverse tangent is 1 over 1 plus x squared. This is, we learned this much earlier in this course, right? The derivative of what you see in the numerator is 1 over what you see in the denominator times dx. So this is an easy substitution once again. So why don't you use that as a hint? Pause the video, and then if you don't remember how that, just find that section when we talked about this kind of derivative, and then use that, and then come back to the video. Okay, so let's take, I'm assuming you've done that. So u, if we take u as the inverse tangent of x, then the du will be 1 over 1 plus x squared dx, right? Which is what we have here, dx times all of that. If you separate these, right? Why don't I do that here? Why don't I do that here and say that that is equal to integral of inverse tangent of x times dx over 1 plus x squared. That, you can write the original expression like that. Okay, you can put the dx inside the parentheses over 1 plus x squared. So we kind of rearrange these terms. The benefit of that, of course, is that we can then associate this piece with that, which is du, and then all of that, all of this becomes u, right? So let's make the substitution. We have integral of u du, right? Very simple. Now, how easy is that to integrate? Very easy, right? So then we have u squared over 2 plus c. Okay, so now, as usual, we need to replace u with what we picked here. So we have, it's going to go off the screen, but it's okay. You know what it is. I'm just going to replace u with that term. So we have tangent, inverse tangent squared over 2 plus c. And we're done with integration very, very quickly and efficiently. Okay, like that. So that was, let's see, that was C. This must be then D. Okay, so here's another example. We want to integrate dt divided by cosine squared t times square root of 1 plus tangent of t, like that. Okay? So one thing that we can do, and dt is here rather than here. I hope you caught a glimpse of that. I would definitely pause here. You've seen enough examples by now. Solve this and then come back to the video. And I'm hoping that you've done that and now you're back. So dt over cosine squared t can immediately be written as secant squared t, right? So let us rearrange this. Before even we use the substitution method, let's rearrange these terms. So we have dt, let me do it this way. 1 over cosine squared t times 1 over square root of all of that, 1 plus tangent t times dt, right? Let's rearrange the terms like that. Now this we know is just what? Secant squared t, right? So let's write it like that. This one, we have secant squared t. And then this piece, we're going to keep that. So we have this piece and then multiplied by that piece, 1 over square root of 1 plus tangent t dt. Okay? So if we take, now our goal is to write one term in terms of the derivative of another term, right? So we know that if we take the derivative of the tangent t is secant squared t. This we know from before. So let me actually write that down. So recall that ddt of 1 plus tangent t is equal to secant squared t. You take the so you take the derivative of this, and 1 drops out, right? Derivative of 1 is just 0. Derivative of tangent t is secant squared t, dt. Okay, and dt is here. You can multiply both sides by dt, and you get the dt on the other side. Okay, so let's take u. Because of this understanding, then we set u to be this, 1 plus tangent t. If that's the case, then we have du is equal to secant squared t dt. And I mean, it's something we have on this side, but this is the same thing as that. I hope you can see, I mean, the same thing as that. But we multiply both sides of that by dt, and dt drops out on the left. We have du, and then on the other side, we have secant squared t multiplied by dt. That's all we've done. Multiply both sides by dt. Okay, then, so in this case, then, we can start substituting from here. So from here to here. Then we have a nice substitution here. We have secant squared t dt is just du, right? This times that is just du. So I'm just going to put du here. What about this term in the middle? That's 1 over, we took this as u, right? So 1 over square root of u. So in the middle, we have 1 over square root of u. Okay? So now, this is really easy to integrate because now that is equal to, that's u2. If you rewrite this in terms of rational exponent, and this is what we learned back in basic algebra, what do you get? You get u to 1/2 power. But this is the reciprocal of that, so you can say u to minus 1/2 power du, right? Just rewriting that in this term. Now, we add, this is easy to integrate. We add 1 to this. We get u to 1/2 power, divide by the new power, which is 1/2. So this is what we're doing. After integration, divide by that, plus c. But of course, this will give us 2 times, right? 2 times u to 1/2 power plus c. Right? So we're almost done. All we have to do is replace u with what we originally had, which is 1 plus tangent of t. So let's do that. So that is equal to 2 times 2 times, let's see, so 2 times 1, and of course this is square root, so square root of 1 plus tangent t plus c. I really didn't need the parentheses here, so let me, I know some of you might think, why do we need that? And you'd be correct. I really didn't need that. If I had my white out with me, I would get rid of the parentheses, but let me just clean that up and write it the right way. So this would be that, because the radical expression itself is a grouping symbol as well as what it does, which is taking the square root of that expression. So that being a grouping symbol by itself, we don't need the parentheses. So this is what we have. Okay? So the parentheses are extraneous, and I'm sure you know that better than I do. Okay, let's see. Okay, so we've done enough application of the substitution rule to integrate indefinite integrals. So I'm sure many of you, if not all of you, are wondering, well, when are we going to get to the definite integrals? As a matter of fact, we're going to do that now, because those are very important too, because they have lower and upper limits of the integration, which will change due to the substitution rule. It will have to change. Okay, so in these examples, we want to evaluate the definite integrals. I hope you're noticing that this statement doesn't specify using the substitution rule. So you could expect, I mean, right now we're introducing a lot of these techniques now, but in Calc 2 and Calc 3, especially in Calc 3, because Calc 2 still involves some additional integration techniques. We've covered quite a bit, but in Calc 2 you'll learn more techniques. But in Calc 3, it's just application of all these techniques you've learned before. So the statement is not going to tell you which integration technique you should use. You should remember to use these methods where appropriate. Okay, just notice that missing, that statement to use the substitution rule is missing. Okay, and it should be. All right, so let's start with this one. We want to integrate from 0 to 1 this expression cosine of pi t over 2 dt. Okay? So let's take, because here the cosine, we can't really substitute for that, right? That's the main function, and it's the only function here. Let's substitute for pi t over 2. So, and again, this is the first example of a definite integral and the substitution rule. So it's okay if you want to pause the video, that'll be up to you, but if you don't, that would be okay, because this is the first example of this kind we're talking about. Okay, so u, if it's equal to pi t over 2, t being the variable, pi over 2 is just a constant, then we have du should be pi over 2, right? If this was 2t, the derivative would be 2. If this was 5t or negative 8t, the derivative would be negative 8. So it's pi over 2t, so du is pi over 2, of course, dt. Okay? So then let's see if we can directly substitute for dt with du. No, we can't, so let's see what we need to do. So dt, so for that, so that's u. So we're okay here. The dt is a problem here, so we need to, okay, so then from here, let's extend this, because we're okay with here, that's fine, but dt, if you multiply both sides by 2 over pi, you're going to get dt on that side, and then on this side you're going to get 2 over pi du. So now we can substitute. For dt, pi t over 2 is just u, so cosine of u. Instead of dt, we have 2 over pi du. And the nice thing about this is that 2 over pi is just a constant. We can pull it out of the integral. Okay, so no worries about this. This is just a constant. Okay, so now let us before I make the substitution, let me also, and I'll write it in blue because this is very, very important. Notice we're switching from t to u, right? So we need to change, because the lower and the upper limits of this integral have to do with the variable t. What about u? What about variable u? What would be the limits of integral for du? Not for dt, we already have that, but for du, we need to calculate it. So if u is equal to, if t, not u, if t is equal to 0, then u, it would be 0 as well, right? Pi over 2 times 0, so u is equal to 0 as well. Then if t is equal to 1, which is the upper limit of that integral, then what would u be? U would be, plug in for t with 1, what are you going to get? Pi over 2. So u would be pi over 2. So the lower limit of the integral, when we have du, is 0, and the upper limit is pi over 2. If you have to slow down to make sure what happened here, do that, because this is very, very important. You're going to see operations like this again and again in future calculus classes. So please make sure you take the time to fully understand what happened from here to here. Okay, when we not only did what we did when we were substituting for indefinite integrals, that's that piece, but we also had to figure out new lower and upper limits of the integral. We had to do that in addition to what we used to do. Okay, now we are ready to write out or apply the substitution rule. Instead of 0, we have 0 again for u. Instead of 1, we have pi over 2. And then cosine of u, and then dt, that whole thing is u, and then dt is 2 pi over 2 over pi du. Okay, so now we can easily bring this 2 over pi out. This is just a constant. 2 over pi times the integral of z0 to pi over 2 cosine of u du. Okay? Now, how easy is that to integrate? Very easy, right? It's just sine of u. The integral of cosine of u is just sine of u. Take the derivative of sine of u, you get cosine of u. Okay, so we get, continuing, we have 2 over pi times sine u going from the lower limit 0 to upper limit pi over 2. Okay? Then the rest is easy. You can just plug in. This is a definite integral, so we have to evaluate sine at pi over 2 minus sine at the lower limit. And what do we get? We get 2 over pi. Sine of pi over 2 is just 1. Minus that is 0. So we simply get the 2 over pi back. 2 over pi. Okay. All of that. I'm sure by now you can see how useful this technique, substitution rule, is. Okay. So let's do another example of this kind with definite integrals. I think that was A. That was the first example. So this one has to be B. Integral from 1 over 6 to 1 over 2 cosecant pi t. And I grabbed this from the end of section 5.5 section exercises. So, and they don't include this in parentheses. I personally have a habit of putting parentheses around this argument because there are too many letters here and it tends to confuse people. But I'm not going to put parentheses because your eyes need to get used to what you see in various books. So I'm just going to leave it alone. But if I was writing this on my own paper, in my own notebook, I would put parentheses around that. And feel free to do that. It's just a visual aid. But I want to stick with what the book did and just write it like that with no parentheses. Okay? But the argument of cotangent function is pi t, and the argument of the cosecant function is pi t. All right, so here, let's see. If we substitute for cosecant, so looking at this, cosine u, cosecant u times cotangent u, if we integrate that, we get minus cosecant u. So that would be great. So everything is all well with cosecant and cotangent, but we need to substitute for pi t. So let's use that. And I forgot to remind you to please pause and carry out your own solution before coming back. But you can use what I said as a hint, but still pause the video. It's worth it if you do that and write down your own solution first. So, because if you integrate this like it is with t, and you have pi here, so it's gonna be a messy integration. So let's replace pi t with u. So u as pi times t, and then du, very easily, it's going to be pi dt, right? Pi dt. So then dt would be 1 over pi du, because we're going to replace dt. So just look at this, look at it as an equation of any kind, solve for dt. What do you get? You get dt, multiply both sides by 1 over pi. Okay, so 1 over pi du. So now we can replace that, and we can replace pi t in both cosecant and cotangent functions with u. So let's do that. But what do we need to do next? Before we rewrite this integral and use the substitution, what do we need to do? You remember? We have to adjust these lower and upper limits of the integration, right? So let's, because these limits are for t variable, not for the u variable. Okay, so let's calculate that. So if t is equal to 1 over 6, let's start with the lower limit. Then substituting here, what do we get? Then u is equal to pi over 6, right? Just substitute for t with 1 over 6, you get u equals pi over 6. Then if t is equal to the upper limit, 1/2, then u is equal to, replace that, what do you get? You get pi over 2. So we found the lower and upper limits of the integration once we switch over to du. Now we can switch over. We have everything we need. Okay. So let me move this up as much as I can. So we have the lower limit is going to be pi over 6. Upper limit is going to be pi over 2. And then instead of cosecant pi t, what do we have? We have cosecant u. Instead of cotangent of pi t, we have cotangent of u. Instead of dt, we have its equivalent, which is 1 over pi du. Okay. All right, let's clean this up a little bit, because 1 over pi is just a constant. Let's bring it out of the integral, and let's write as 1 over pi. At least I prefer to do that before I carry out the integration. Okay, and then we have du. Okay, now that's cleaned up, and now we can easily see what the integral of this expression is. Let me write this down. Recall that derivative of derivative of that derivative of minus cosecant of x is cosecant x cotangent x. So the derivative of that is that. And here we have, so we have that. So right away then we can use this to integrate this expression and get minus cosecant of u. Okay, thus, so from here we have 1 over pi and times minus cosecant of u, because our variable is u, not x, and then of course going from pi over 6 to pi over 2. Okay, all right. So now I prefer to, every time I have secant of x or cosecant, I prefer to rewrite them in terms of their reciprocal, or in terms of sine and cosine. So in this case, we have let's write it like this. So equals 1 over pi minus, it's just easier to work with sine and cosine than cosecant and secant. And sine of u, and then pi over 2, pi over 6. The other thing we have to do, so because, notice that in this case, because we've already found the lower and upper limits of the new variable u, we don't have to convert this back to the t variable, which is what we started with, right? We don't have to do that. We only have to do that with indefinite integrals. But here, we've already converted the limits, lower and upper limits for t to lower and upper limits for u, so we can substitute directly. We don't have to go through t anymore. Okay, so let's do that. So we have 1 over pi, and then minus 1 over sine of pi over 2 minus 1 over, let me move this up, it's better, minus sine of pi over 6, like that. Okay, so sine of pi over 2 is easy, it's just 1. So this would be minus 1 in here, then minus here in the middle. Then we have sine of pi over 6 is 1/2. 1 over 1/2 is 2, so we have minus 2 in here. So then we have minus 1 plus 2 is just 1. 1 times 1 over pi is just 1 over pi. Like that. Okay. All right, so that's another example of the definite integral kind. Let's do another example of this kind, and that was part B. So this will be part C. We want to carry out this definite integral of the natural exponential function e to the z plus 1 divided by e to the z plus z dz, all right, like that. Okay, so why don't you just pause and see how far you can get with this. Pick something to substitute for, and see which part of this integrand can be written in terms of the derivative of the other piece. Right? That was the original idea before we can apply the substitution rule. Okay, so I'm assuming that you guys have done that, and now you have your own solution written down, and now you're back. Okay, so if you take a look at this, you know that the derivative of what's in the denominator, e to the z plus z, the derivative of this piece is what's in the numerator, right? Because the derivative of the natural exponential function is itself. So e to the z has derivative e to the z plus the derivative of z will be 1. So the derivative of everything in the denominator is what you see in the numerator. So let's set u equal e to the z plus z. Therefore, we know that then du would be e to the z plus 1. Plus 1, of course, dz. Okay? Look at that. I mean, it's e to the z plus 1 dz. Right? So it's an easy substitution right there. What do we have to do next? If you've done your own work already, you should know what we're going to do next. We're going to have to do next, right? We've switched from z, variable z, to u, so we need to change, we need to figure out what the new limits of integration are for the new variable u. We can't stick with this, okay, because these belong to the old variable z. We have a new variable u. Okay, so let's do that. So if z equals 0, then what do we get for u? Then u will be e to 0, that would be 1, plus 0, which is 0. 1 plus 0 is just 1. So that's the lower limit for variable u. Then if z equals 1, right, then what are we going to get? Then we're going to get u equals e to the z, which is 1. So I'm just going to write it as e to the 1 is just e, plus z, which is 1. So that's our upper limit. Lower limit is 1, upper limit is e plus 1. Okay? So now we can easily go ahead and switch over from z to u. And that's going to go, well, maybe I can still keep it on the screen like that. So we'll have, we're switching to u, right? So the lower limit is 1, not 0 anymore. And then the upper limit is e plus 1, not 1 anymore. So e plus 1 is the upper limit. And of course, that would be then substituting for the rest of it. We have 1 over u, because e to the z plus z is what we picked. 1 over u, and then e to the z plus 1 dz was du, which is that, all of that. So du. Okay? That's pretty simplified. I mean, look at that, compare it with what we have. Much, much more simplified, right? Okay, great. So now let's do the integration. Integrating 1 over u is going to be natural log of u, because the derivative of natural log of u is 1 over u. So we have natural log of u going from 1 to e plus 1. Again, we don't have to look back at z anymore, because we have the lower and upper limits figured out in terms of u. All right? Okay, great. So let's plug in. We have natural log of e plus 1 minus natural log of 1. And what are we going to get? That piece is 0, right? Natural log of 1, we know it's 0. So we end up with natural log of e plus 1. Like that. All right, let's do another definite integral example. So that was C, this is D. So we have integral of going from 0 to 1/2 of inverse sine of x divided by square root of 1 minus x squared dx. Okay, if you haven't done this already, please pause the video, figure out this solution, and then come back to the video. Well, I mean, recall that if you take the derivative of the inverse sine of x, what do you get? You get 1 over square root of 1 minus x squared. So let's write that down. So recall that derivative of inverse sine of x is equal to 1 over square root of 1 minus x squared. Right? We know this from the past. Now, if you multiply both sides by dx, you're going to get the dx on the other side. So inverse sine inverse sine of x is equal to dx over square root of 1 minus x squared. But this is important to remember, because as soon as you remember this, then you know what for which term you need to make a substitution. Right? So you set u to be inverse sine of x. So u is equal to inverse sine of x. Therefore, du is all of that 1 over square root of 1 minus x squared dx, correct? Okay, so look how easy that made this expression, or this integral, because dx divided by square root of 1 minus x squared, which is what we have here, is equivalent to du, and inverse sine of x is equivalent to u, right? So we're already figured this out for this piece, but what about the limits? The limits of the integration, we need to also figure those out. So if, it's just 0 to 1/2, right? So if x is equal to 0, which is the lower limit for dx, then substitute it here, what do you get? What angle has sine equal to 0? Because you know from basic trigonometry, we know that this is an angle, right? The inverse trigonometric function is always an angle. So here we're looking for, if you substitute for x with 0, if you take the inverse sine of 0, then you're looking for an angle for which the sine is 0. So that would mean u in this case, which would be that angle, is equal to 0. If x is equal to the 1/2, the upper limit of the integral for dx, if x equals 1/2, then you're looking for inverse sine of 1/2, which means you're looking for an angle x such that the sine would be 1/2, and that's pi over 6, right? So u is equal to pi over 6. So we figured out the lower and the upper limits of the integration for when we use the u substitution here. Okay, so let's then, after all this, we can then, and I'll move this page up. I know you can't see the original integral, but it's okay. I'm going to post these notes on Canvas, so you're going to be able to follow it if you download the notes. But we're going to replace this with u over dx over that. It's du. So it's a very straightforward substitution, u du. The upper and the lower limits of the integration are 0 to pi over 6. right? Okay, so now let's see what do we have. We have u squared over 2 going from 0 to pi over 6. So if you substitute, you get pi over 6 squared over 2 minus 0 squared over 2, right? So what is that? That's pi squared over 36 over 2. So you have pi squared over 36 times 2, that's 72, and that's just 0. So this is what we have. Pi squared over 72 is what we have. Okay, the final integration result. So your book talks about the average value of some function using this method, and let's just give one example of like that too. All right, so this is the average value of the given function is something that we introduced or discussed the formula for in the previous section. And now it's good to have one of these examples as well so we can look back at what we learned in the previous section. So recalling that formula, we have this is how we would apply it. We'd have the, so basically the interval 0 to pi tells us the limits of the integration, lower and upper limits of the integration, because that formula for average value of the function involves an integral. And we had, this was the formula, 1 over the difference between the upper and lower limit of the integral from lower to upper limit of this function. Okay, that's the formula for us to use. So using the method of substitution rule, then it's easy to see, and we've actually done one example like this before, that sine of x is the derivative of the cosine of x. So let's take u as the cosine of x, and then immediately du is has derivative minus sine of x dx, right? Minus sine of x dx. And then, of course, if you look at this, we can't immediately substitute du here because we have minus sine of x, but this original expression is positive sine of x dx. So let's multiply both sides by a negative. So minus du is equal to sine of x dx. Now, if you compare this with that, then we know we can replace sine of x dx with minus du. And of course, the cosine of x with u. Okay, so the other thing that we have to do, which I'm sure you know, is to figure out the lower and upper limits of integration for the new variable u, because these are for x and dx. So if u is equal to the lower limit of integration, 0, if you plug it in here, we have cosine of 0, so this will give us cosine of 0 would be 1, or therefore u, well, let me let me correct this. If x is equal to 0, right? If x is equal to 0, we're figuring out the value for the lower and upper limits of the du integral. So if x equals 0, then u would be equal to 1. If x is equal to the upper limit of the integration pi, then u cosine of pi is equal to minus 1. So something interesting happens here. Let's put it all together, and I'm going to put that here. So if we convert from dx to du, what we will have is 1 over pi, right? 1 over pi minus 0 is just 1 over pi. When we substituted for x with 0, we got what? 1. When we substituted for x with pi, or the upper limit, we got negative 1, right? Let me bring this down a little bit. So notice that the upper, I've substituted for what we found by replacing x with 0 and pi with what we got for u. But if we leave the integral like this, the upper and lower limits are not correct. The lower limit should be smaller than that. We'll take care of that next, but let's complete this integral. So then we have cosine of x was u, so cosine to the 4th power would be u to the 4th power times minus du, right? Because minus du is equivalent to sine x dx, so times minus du. Okay, great. Now we need to fix this so that 1 is up here and minus 1 is the lower limit. And we know how to do that. We simply multiply this integral by minus 1. And that will make this minus du disappear. So minus times minus positive. But let's take it step by step. Minus 1, we're multiplying this whole thing by minus 1, and that will switch. It will correct the limits of the integral. So from minus 1 to 1, u to the 4th minus du. Okay, so minus times minus, it'll be a positive. And then we have 1 over pi integral from minus 1 to 1 of u to the 4th du. Okay, and this is an easy integral to integrate. So we will have 1 over pi times u to the 5th over 5 going from minus 1 to 1. Right? And then the other thing that we could do, actually, and I should insert that here. Recall from the previous slide, and I think we talked about this, and maybe on page 2. Let me bring this back. Recall that if we have, for symmetric functions, if we have negative a to a of some function, we can write that, which is what we have. We have negative 1 to 1, right? We can write that as 2 times 0 to a. In other words, we can switch from the negative lower limit to 0 and then keep the upper limit as what it is, but multiply that integral by 2. Okay, so this integral is twice the integral from 0 to a. So this is the same, because the lower and upper limits are the same distance from 0. That's why we can do that. So recall, so let me recall that, so minus, I'll just reference that second page, is equal to twice 0 to a of f of x dx. Okay, recall that Therefore, we can multiply this integral by 2, and we can switch this lower limit to 0, from -1 to 0. Just recalling that identity. So what we have here, everything here, well, this lower limit, we would keep it as 0. We would change it to 0. Just, I wanted to apply this because we introduced it and we never used it. So this would be an appropriate place to use that. Even though you could continue with -1 to 1, you'd get the same result, but let's apply that identity that we introduced earlier. Okay, and then of course this one will also be 2 times all of that. Okay, great. So what are we going to get? We're going to get 2 over pi. So we're going to get 2 over pi, and then 1 to 5th power over 5 is just 1 over 5. And then minus 0, that would be 0. So we have 2 over positive 2 over 5 pi. Okay, so that would be the result of that. So I could have continued with with these limits for u, but I decided to apply that, and this is just applying that earlier identity. So I hope this lesson was useful, and I thank you for watching it to the end, and have a nice day. And I guess soon after this lesson, you will have your final exam.